talk about it. So just to let you guys know where we are, it's a little bit complicated, mostly by the fact I proved the law of sines and cosines before test 2. So those are actually, chapter 8 topics, right? Section 8.1, 8.2 are law of sines, law of cosines. There's a little bit more in 8.2 that I haven't covered yet that I'll probably cover next week, just say that. And I think we covered section 8.3, which is polar coordinates last time, pretty well. And I started to cover 8.4, but I really just used the computer to do that, So I should come back and talk more about 8.4, about how to graph things, sort of hand-to-hand combat-wise. And the book is okay, but I think it's missing a particular concept which I've found helpful to graph. And so I will attempt to talk about section 8.4 probably next Monday. So what I'm talking about today is actually 8.5. And it doesn't really matter in terms of like the logic. These things are not based on each other, right? So you could talk about them in any order in some sense, but that's not entirely true. But anyway, let's get to it. So today I want to talk about complex numbers. Complex numbers and trigonometry. All right. So I think to start with, since you guys may or may not be familiar with complex numbers, we should talk a little bit about complex numbers. What is a complex number? Well, I use the symbol C for the complex number system. It's things of the form a plus bi, right? Such that a and b are real numbers and I squared equals to -1, right? This is the complex number system. How do we multiply complex numbers? Well, here's how it goes. If you have a plus bi times, really? Min, I'm teaching. Okay, talk to you later. Yeah, bye. That's Min. I'm hoping he's calling me to tell me he got a job offer or something. That would be great. I have to call him back. Anyway, a plus bi, or at least got an interview somewhere. A plus bi, x plus yi. So how do we multiply complex numbers? Just like normal, right? So the way it works is you like a times x plus yi, right? Plus bi times x plus iy. So distributive property, and then you distribute through, so you get like ax plus ayi plus bix, right? And then over here we've got plus I squared times by, right? So I'm just distributing, right? But remember, I squared is -1. So what we have is a times x minus b times y plus I times ay plus bx. So technically speaking, depending on how you approach this, what I just wrote down at the bottom actually serves as the definition of complex multiplication. This times that is that. That's that. You could take that as a definition if you like. But if you take that as a definition, you can prove that complex number multiplication is associative, it's commutative, it has all the regular properties that real number multiplication does, with the exception that I squared is -1, right? We can't have the square of a real number equal to -1. So the thing you lose with complex numbers is ordering, right? Ordering. What's ordering? So if I tell you 3 and 5 and I ask you less than or greater than, right? You can tell me 5 is the bigger one, right? But the thing is, if I do I and 1, there's no standard way to say one's less than or the other. So the complex numbers are not ordered in a natural way, all right? So not less than or greater than, like we just don't even entertain the question with complex numbers in the standard coursework, all right? However, we can visualize complex numbers, all right? We can visualize complex numbers as follows, and the visualization has been around since at least the time of Gauss, probably Euler, really. And so here's the way it works. You just have A comma B. Well, that's identified with A plus BI, all right? So this is the way we plot complex numbers in the so-called complex plane. So this is the real axis. This is the imaginary axis up here, all right? So like the real part of A plus BI is equal to A. The imaginary part of A plus BI is equal to B. And what's that? Not BI. Very good question. Yes, the imaginary part is itself a real number. It's the coefficient of I, but it is real, yes. It's one of those places where the name doesn't quite match people's intuition, yeah? I see students throw the I into that all the time, but it's not correct. So just to give you a few examples, for example, if I do this point right here could be, for instance, 3 plus I. See, because I go over 3 and up 1. I guess I should probably put it here. I don't know, up to the limits of my measuring things on the fly, right? 1, 2, 3 units over, 1 unit up. I failed. So it's down here. I don't know, eventually you get the idea. I can't do very good measuring on the fly here, but that's 3 plus I. Let's see here. So like this point right over here would be minus 1 plus I, right? Another example, if I just had 2 is a complex number of a really silly type. Like real numbers we can look at as complex numbers with imaginary part 0. In contrast down here, minus 2I, this is called a pure imaginary number because it has no real part. So these are some different examples of complex numbers in the complex plane. Mm-hmm. I is a notation introduced by Euler, I think, in 1777. It is a notation for the square root of minus 1. So that's not really answering your question. Like, what is I? It is an object such that the square is minus 1. It is not a real number. It is something new. So when you take the real number system and you adjoin to it something that has this form, the square root of minus 1, you get the complex numbers, is basically it. Other things we can say about complex number system, let's see here. So in the complex number system, right, we can also talk about distance. Or, well, let's talk about the length of a complex number. Or sometimes your book calls it absolute value. I don't typically use that language. I typically call the length of a complex number its modulus. But anyway, here it is. If you think about a complex number, if it's at like, x plus iy, well, how far is that from the origin? That's going to be the length of the complex number, right? By the way, if we use x plus iy for the complex number, then you could think of x, the real axis is the x-axis, the y-axis is the imaginary axis, okay? But of course, this distance is x, right? I mean, this coordinate's x, this distance y if we're in quadrant 1. But it's always true that the length, so we use this notation bar for the length like this, just like absolute value, square root of x squared plus y squared. So this is the length of a complex number. by the way, in the real numbers, if you want a formula for the absolute value of x, it's the square root of x squared. So it's really just continuing the pattern, adding one more term, you know? So that's kind of neat. I don't know if you knew this or not, but that's a formula for absolute value. It's equal to minus x if x is less than 0, and it's equal to x if x is greater than. And you could throw equality into both cases. They both agree. But all right. So this is the length of a complex number. So for example, if I have this number here, I'll call it. We typically use z for complex numbers. Like a lot of time we use z and w. Because we like to use x and y for the imaginary and the real and imaginary parts, you know. So I try not to use x for a complex number. I try to use like a z or a w or something else kind of funky. Anyway, but if this z is, I don't know, let's say minus 3 plus 2i, we can calculate the absolute value of it. The length of this complex number is the square root of minus 3 squared plus 2 squared. All right. The I doesn't figure into it. The I just kind of is a placeholder in some sense. So that's 9 plus 4, which is, square root of 13. The complex number minus 3 plus 2i is square root of 13 distance away from the origin. All right. So that's an example. Now, there's something else which is called the complex conjugate. And so this is by definition z bar. Well, let me say if z, I need to start it out. If z is equal to x plus iy. All right, so let us adopt the custom that if I write z equals x plus iy, I am assuming that both x and y are real numbers. Okay. I often will write that explicitly in problems that I assign and notes that I write, but that's the custom of people. People usually write z equals x plus iy, and they don't say, oh, by the way, x and y are real numbers, but they mean it. That's just a common, yeah, it's a custom. So if this is z, then the conjugate of z conjugate is x minus iy. So graphically, it's pretty neat. What's going on here is if you got, if you got x plus iy up here, or if you've got, x 2 plus iy2 over here, where's the conjugate going? See what it's doing? The x stays the same, and it just flips. And I should have put, my other example should be down here. That's more interesting, yeah? So it keeps the x the same, and it just, flips it over the, flips it over the x-axis, flips it over the real axis. So, yeah, the complex conjugate flips complex number over the real axis. Incidentally, this gives us the kind of neat way to define a real number. All right, so definition, if z in the complex number system has z bar equals to z, then z is real number. I mean, you could take that as a definition, but you don't have to. I mean, anyway, you could make it a theorem if you like. It is true, though. If something is equal to itself under complex conjugation, it's real. So, and if it's equal to minus itself under complex conjugation, it's pure imaginary, actually, right? All right, so It turns out that the complex conjugate has really neat properties. Let's work one out. So suppose z is, x plus iy, and w is a plus ib, all right? So first of all, z plus w is x plus a plus I times y plus b. I'm grouping things, right? So the complex conjugate of z plus w is x plus a minus I times y plus b, right? But we can rewrite that. That's x minus iy plus a minus ib. So that's z conjugate plus w conjugate. So the complex conjugate of a sum is the sum of the complex conjugates. So that's one property of complex conjugation. That alone is pretty neat. But what is really, really one of the things that makes complex numbers so special is if we look at z times w, right? So that's x plus iy times a plus ib, right? Multiply that out, you've got your xa minus yb plus I times, xb plus ya. So that's the product of z times w. What's zw conjugate? The complex conjugate of all of that, of course, is same thing, but minus the imaginary part, right? So let's keep that in mind, and you can contrast that. What happens if we do z bar times w bar? So z bar is what? X minus iy. W bar is a minus ib. So let's multiply those out. What do we get? You can multiply them while I move the camera here. So you said you got xa and minus, but notice that gives you a plus, but you still have the I squared.
Right, which would make it positive 1.
Well, the I squared is minus 1, so you get like a I squared yb. That's minus yb for that term.
And then
Yeah, then minus I times ya, right? And the other one's plus xb. I got the minus out here. But look at this. This, right? I mean, compare this to that. And compare this to this. So like one of the fundamental things about complex numbers is two complex numbers are equal if and only if they have matching real parts and matching imaginary parts. It's because they're essentially points in the plane, right? 2 points in the plane are the same point if and only if they have the same x and y coordinates. So like that's the same here. So these are equal, which gives us the following theorem. The conjugate of a product is the product of the conjugates. This is a very nice property of complex conjugation. Also, I should make a remark. If we calculate z times z bar, that's x plus iy, right, times x minus iy in our current. So that gives me x squared minus xiy plus iyx minus I squared y squared, right? But check out what happens to the middle terms. cancel. And what do we get? We get x squared plus y squared. What is that, though? That is the length of the complex number squared, right? So in our notation we introduced about 10 minutes ago, this is straight vertical bars z squared. And this actually reveals to us how we can find the inverse of a complex number in the multiplicative sense. So this tells us that if you solve this for 1 over z, right? 1 over z equals to, what is it? Z bar over the modulus of z squared, the length of z squared, right? So this is a formula. This is how to calculate reciprocal of complex number, right? Now, that's how to calculate the reciprocal of a complex number. Let me actually work an example of that. That's not quite how we typically look at it, by the way. I mean, that's not wrong what I wrote, but I'll show you how people typically do this kind of thing. All right, so, I mean, the formula I just wrote down, what that shows, among other things, is that if the complex number is non-zero, right, then it has a non-zero length, and that's a formula for its inverse. That means that every non-zero complex number has a multiplicative inverse. That's part of what makes the complex number systems what's called a field. So let's find Cartesian form of 1 over 3 plus 4i. Now here, the Cartesian form of that means to put this in the form a plus bi. We have to find a and b to rewrite it like that. Okay, that's what it means to put it in Cartesian form. Hopefully before the end of the day, I'll talk to you about what we mean by the polar form of a complex number. So, so here's the plan. We have 1 over 3 plus 4i, right? And what we do is just multiply that by 3, the conjugate, over the conjugate. So multiply by the conjugate over the conjugate, like that, conjugate of the denominator. And what we get, of course, is 3 minus 4i. And downstairs we get 3 squared minus 4 squared I squared, right? Because you notice that the cross terms of 12i and minus 12i cancel downstairs. And this is not an accident. So what we're looking at here is 3 minus 4i. That's 9 plus 16, which is 25. Because remember, I squared is minus 1. So in short, 1 over 3 plus 4i is 3/25 minus 4/25 times I. In other words, the real part of 1 over 3 plus 4i is 3/25. And the imaginary part is, yeah, negative 4/25. Yeah, because, exactly, I squared is minus 1. And the cross terms here cancel. That's the magic. So that's the beautiful thing, right? So the typical pattern is this. We have 1 over z, right? Well, that's equal to 1, that's equal to 1 over z times z bar over z bar. All right, because if z is not equal to 0, if z is not equal to 0, then z conjugate is also not equal to 0, so we can multiply by z conjugate over z conjugate, and in so doing, we get the formula z bar over z bar. What z bar is, that's exactly the thing we derived on the other board. See that? It's the conjugate over the magnitude squared. The other word for length of a complex number is just magnitude. We can think of it as a vector, it's its length. And that's exactly what we had here. The length of 3 plus 4i is 25, is 5 because it's the square root of 25. And then you square it, you get 25. So like the length squared is 25, and that's the conjugate. So this is often taught in like high school algebra, like how to do this part of the complex arithmetic, right? But I think often it's just sort of taught as a, well, this is a lot like the following calculation, right? To rationalize the denominator of that, we multiply by the conjugate. But this is a different kind of conjugate, isn't it? It's just, in that case. So you get, 3/7 plus 1/7 root 2. But it's the same kind of mathematics, is true. Actually, these are actually part of a deeper mathematics, both of them are. But anyway, let me not talk about that here. Now, of course, if you're one more example like this, just to make sure I've done enough that you. Well, just another example I think is healthy, just to get a little bit more used to this complex arithmetic, right? So, example, find Cartesian form of, 3 plus I over 2 minus I. Right? And I'll call this thing, well, let me not give it a name. Fine, I'll call it Z. All right? So Z is 3 plus I over 2 minus I. Now, how am I gonna get that I out of the denominator? I multiply both by the conjugate of the denominator over the conjugate. So I multiply by 1 in the appropriately chosen way, like that, right? But the difference now is I actually have to multiply out the numerator. The denominator is easy. We know it's just the length of 2 minus I squared, which is going to give me 4 plus 1 is 5. So you get a fifth upstairs. So let me just get that over with. 5. 2 squared plus 1 squared is 5. That's how that multiplies out. But the numerator I need to actually work out, right? 6 plus 2i plus 3i minus, plus I squared, right? Divided by 5. So that's 6 minus 1, which is 5. And I've got 5i divided by 5. Whoa, cool. This is 1 plus I. Yeah, that's actually really interesting. I mean, because I get 5 over 5, yeah. That's not what I was expecting. Huh. Interesting. All right, so last time, so everything I'm telling you here is very interesting in of its own right. Obviously, there's a game you can play which is for equations that are in the Cartesian plane in terms of x and y, can you write those equations in terms of like z and z bar, you know? I guess I should probably mention that this is maybe a little bit off the track, but beaten track for us, but so we have z is equal to x plus iy, right? And z bar is equal to x minus iy, right? Can you solve those for x and y? What happens if we add those equations? Z plus z bar. When we add, the plus and minus iy's cancel, and we get 2x. When we subtract, we get the x's cancel, and we get 2iy. Right? So this gives me that x is equal to 1/2 of z plus z bar. And this gives me that y is 1/2i z minus z bar. For what it's worth, this is a formula for the real part of z, and this is a formula for the imaginary part of z. But it's also a roadmap on how to convert a Cartesian equation in the plane for a corresponding complex equation. But I'm going to resist the urge to get into that. That's something we tend to do in complex analysis, so I'll leave it for there. Okay, so we talked about polar coordinates last time, right? So how does polar coordinates and complex numbers go together? What's the story there? Well, here it is. So if I have this, x plus iy, right? And I want to write that in terms of, what is x equal to? X is equal to our cosine theta, right? Y is equal to our sine theta, right? If I'm calling this point z, right? Saying z is equal to x plus iy. R is the length, is the distance from the origin to the point, right? That's this r. But what else is that? We called that the absolute value of z, right? So r is equal to the length of z, right? So wait a minute. So what we have then is we have z is the absolute value of z times cosine theta, right? Plus I times the absolute value of z sine theta. Right? So all I'm doing is I'm plugging in this equation into here and this equation into here. Now, the next step is to factor out the length of z like this and write cosine theta plus I sine theta. So your book has a name for the thing I just wrote down in terms of sine and cosine. Your textbook likes to call what I just wrote down. Well, let me just give you the definition here. So definition, cosine theta plus I sine theta. They like to call this CIS theta. This is probably the last time I'll write that in here. I do not like this notation. I don't think it's healthy. I don't think it's good. And that's the reason I'm rewriting the homework from that section, because I do not want to encourage the use of this notation. There is a better notation for this, which is common to all of higher mathematics, and that is to use the following notation. Cosine theta is simply this. E to the I theta is cosine theta plus I sine theta. This is the so-called imaginary exponential. So this notation, I think, dates back to Euler, actually. And it's one of the most beautiful notations in mathematics because of how much it contains in it. This is something new. You've only talked about exponentials of real numbers before. Now I'm talking about this is the exponential of an imaginary number. All right? So for this to be legitimate notation, that means that they must have some kind of connection with the ordinary exponential you're used to, right? What are the laws of exponents that you know? Remember, you know, like e to the, e to the x, well, e to the s to the t is e to the st, right? And if you had like e to the alpha times e to the beta, e to the alpha plus beta, right? So these are the two big ones. Other thing, like e to the 0 is what? 1, right? So let's start picking on this definition, see if it works. How about e to the I times 0? Well, that's going to be, by definition, cosine of 0 plus I times the sine of 0. Is that true? Well, sine of 0 is 0. Cosine of 0 is 1. Looks like we made it. Now, how about this one? How about this law of exponents? So let's try it. E to the I theta. Tell you what, let me write it where you can see it better over here. I keep working myself over to the corner. So we have, let's try e to the I theta times e to the I beta. Let's work that out. How's this work? So by definition, remember, by definition, this is cosine theta plus I times the sine of theta. And this is cosine of beta plus I times the sine of beta. Now, so we multiply, and we've got ourselves cosine theta, cosine beta, and then I'm going to do the next one. What's I sine theta times I sine beta? It's I squared sine theta sine beta, right? So it's minus sine theta sine beta plus I. What are the terms with I? Well, you got cosine theta cosine beta, and you got your sine theta cosine beta, right? I feel like I did something. They both have. Oh, 1 second here. I think I did that wrong. Cosine. Oh, it's supposed to be cosine. It's like something is wrong. There it is. It's supposed to be cosine theta sine beta, sine theta cosine beta. There it is. Okay, so what's that? Do you recognize those? See, we have proved in this class that those are the adding angles formulas for cosine and sine, respectively, right? This is straight up cosine of theta plus beta, and this is the sine of theta plus beta. And by the definition we just made, that can be written as an imaginary exponential, right? That is the imaginary exponential of I times theta plus beta. In other words, it's e to the I theta plus I beta, right? I mean, this is the law of exponents that we wanted to be true. We can add exponents when we multiply the product of imaginary exponentials. This is very, very neat. This means somehow the ordinary, just plain Jane law of exponents for imaginary arguments somehow encodes both the adding angle formula for cosine and for sine. But we know that the adding angle formulas for sine and cosine derive pretty much all other trig identities. This gives us great hope that these formula, this imaginary exponential formula, paired with the assumption it obeys the laws of algebra, which we now see are eminently reasonable, it means we can derive a lot of things. Maybe. Now, to prove this last one here, it's a little bit slipperier, but I'll just say this. For the sake of time today, I'll just say we can show that e to the I theta raised to the n power is equal to e to the I n theta for n equals to 1, 2, 3, This is known as de Moivre's theorem. I can't say de Moivre, so I just mispronounce it. All right. That's just kind of a passing comment here for today, but what I want to show you is in the same way all right, so there's a lot more to say here, more than I have time for today, so I'm just going to say the most interesting thing. So cosine theta, e to the I theta is cosine theta plus I sine theta, right? By definition. What happens if we replace with minus theta? E to the minus I theta, that's cosine of minus theta plus I times the sine of minus theta. But what do we know about cosine and sine? Well, we know cosine's even, sine is odd, so cosine e to the minus, and sine doesn't, right? Right. So what happens if we take this, and we take that, right, which are respectively e to the I theta, e to the minus I theta, we add them, what do we get? Well, the sine theta terms cancel, right? And we get, right, which is kind of neat. On the other hand, if we take their difference, we get the cosines cancel, and we get 2i sine theta. So we actually can find formulas for cosine and sine. See, this tells us that cosine theta is 1/2 e to the I theta plus e to the minus I theta, and sine theta is 1/2i e to the I theta minus e to the minus I theta. Do you happen to remember the formulas for cosh and sinh? Well, if you did, I'll remind you. Cosh x, 1/2 e to the x plus e to the minus x. Sinh x, 1/2 e to the x minus e to the minus x. Not an accident, all right? There is always an interplay between the hyperbolic and the circular functions, like cosh and sinh and cosine and sine. I definitely shouldn't have erased something I just erased there. But what I want to show you, two things for the time that remains, I think. 4 minutes, okay. 4 minutes should be enough. So the one thing is now that we have this like really nice notation, we can rewrite the polar form, and we'll talk a lot more about this next time, but first of all, so if z is equal to x plus iy, and the standard angle of x comma y is theta, then we can write z as the length of z times e to the I theta. So this right here is the polar form of a complex number. Magnitude and angle. That's one thing. Well, I have much, much more to say about that. So I'll either talk about it Monday or Tuesday, depending on what happens. I still need to talk more about graphing polar equations, like I said. So that's one thing. The other thing, of course, is that we can use e to the I theta algebra to derive trig identities. Let's take it out for a spin. Cosine squared theta is what? Cosine times cosine, right? You're like, well, I know the identity for that because we worked it out already. Well, that's great. Imagine yourself in a world where you've already forgotten the identity. Check this out. So what I do is 1/2 e to the I theta plus e to the minus I theta. 1/2 e to the I theta plus e to the minus I theta. And now I just multiply it out. So I get 1/4. And I'll write it out. So I e to the I theta, e to the I theta, plus e to the I theta, e to the minus I theta, plus e to the minus I theta, e to the I theta, plus e to the minus I theta, e to the minus I theta. Once you get good at these, you don't have to write all those out. But you see what's going on here. These two, what happens when you have e to the, what happens with these? Like, by the thing we just proved, right? By the over there, the beta equals the minus theta case, e to the 0, we get 1. So this is 1, this is 1, and so what you got is 1/4 of 2 plus e to the 2I theta plus e to the minus 2I theta, because I can do the adding exponents on this and that the same. One more step here, pull a half out. So that's 1 plus 1/2 e to the 2I theta, e to the minus 2I theta. What is that, though? See, this right here, applying the formula I have boxed over there, replacing theta with 2 theta, recognize this is cosine of 2 theta. See, it's the same pattern, just theta is replaced with 2 theta. So that makes this cosine of 2 theta. So what we have is 1/2 of 1 plus cosine of 2 theta. This is the half angle identity for cosine squared, or the double angle identity, depending on how you talk about it. But it's not something I've derived in some sort of circuitous fashion from adding angles formulas. I put down the thing I want the formula for here. I convert to imaginary exponentials. I do regular algebra on exponentials and just rewrite things in terms of what I'm looking for. This is a way of, like, you can derive about 50% of the formulas that we have written on that formula sheet using this technique. So that's what I was talking about. But anyway, much more to say next time. Sorry if I went over. Everybody who came today gets 10 bonus points. Woohoo!